All right, we're jumping ahead a little bit here, and we're going to talk about understanding the results of hypothesis testing and the general idea of hypothesis testing before we get into the details that is covered in 9.3, 9.5, and 9.6 of actually performing the hypothesis tests. So this is kind of a overview of what we're going to be doing. Let's start with an example. Suppose a baker claims that his bread height is more than 15 centimeters on average. Several of his customers do not believe him. To persuade his customers that he is right, he's going to perform a hypothesis test. First step is let's go ahead and figure out what are the null and alternative hypotheses. You've practiced this before. Pause the video and write down the null and alternative hypotheses. All right, are you back? Well, he claimed that the bread height is more, that is so annoying, is more than 15 centimeters. Okay, so that is an alternative hypothesis since it does not have an equal sign. So his claim is the alternative hypothesis that mu is greater than 15. And the contradictory hypothesis to that would be that the mean bread height is less than or equal to 15 centimeters. So what does he do next, now that he has his null and alternative hypotheses? Well, he bakes 10 loaves of bread and calculates the mean height of these sample loaves to be 17 centimeters. The baker knows from baking hundreds of loaves of bread that the standard deviation for the height is going to be a half centimeter, and the distribution of the heights is normal. The question for us and for the baker is how unlikely is it that a sample of size 10 would have a mean height of 17 centimeters given that the null hypothesis is true? So if we assume that the null hypothesis is true, and what would we say it was, that the mean is going to be 15 or less, how unlikely is it that he could have this sample of 10 loaves that had a mean of 17 centimeters? And that's really what we're going to be getting after with hypothesis testing. The next step to getting forward with this is to write down what we know about these bread heights. Well, we know the population standard deviation, sigma. It's equal to a half centimeter. Excuse me. That was given to us in the question. If the null hypothesis is true, which we're going to assume it is, then the population mean, mu, is 15 centimeters. The sample mean was calculated to be 17 centimeters. And we know from our work, from the central limit theorem, that the sample standard deviation is going to be sigma divided by the square root of n, which in this case is going to be 0.5 divided by the square root of 10, which is about 0.16. All right? So if we assume the null hypothesis is true, this means that the means of the samples of size 10 for bread heights are distributed normal, with the mean at 15, the mean stays the same, and our sample mean standard deviation, which is equal to 0.16. Now, using this normal distribution for the sample size 10 of bread heights, we need to look and see how unlikely is it for this value to be 17 or higher. If we have a sample size 10, how unlikely is it for the bread heights average to be 17 or higher? Well, let's look at our normal distribution for mean 15, standard deviation 0.5. And if you look at the cumulative probability of being 17 centimeters or higher, that would be from 17 to infinity. I calculated this ahead of time on Desmos, so you can go do it. It's pretty darn small, 0.00003. And in fact, it's so small down here that I couldn't even really zoom in enough for you to see it, right? It's more than 17, so it would be like this bit in here, right? Would be between the area, between the curve and the axis in this area. You can't even see it. It's such a tiny probability. So when we assume the null hypothesis was true, so that we could say that the means for the sample size of 10 bread heights are in fact distributed normal 15.16, we figured out that it was very unlikely for the value to be 17 or higher. In fact, we got the probability, that should be x bar, that x bar is greater than 17 is equal to 0.0003. In fact, maybe there was 4 zeros. There's 4 zeros. 0.03. Still really small. So we reject the null hypothesis. All right? That is very, very unlikely that by pure chance that the mean of those loaves would average 17 centimeters or higher if in fact the load's average height is 15 or less. So it is very unlikely that this would happen at random chance. So we don't think the null hypothesis is true. This evidence strongly supports that the mean height for the loaves of bread is more than 15 centimeters. All right, so the next question we need to answer is how unlikely is unlikely enough? And the quick answer is that it's usually given to you how unlikely it needs to be. The probability we just calculated is called the p-value. In this last example we did with the loaves of bread, the p-value for a 17 centimeter mean for 10 sample size 10 loaves of bread was equal to 0.00003. It's obviously a very low probability of this happening. You are usually going to be given a value for alpha. Remember, that is the probability of a type 1 error. That means that you accept that the null hypothesis is true, but you've rejected it. All right. And that is called the significance level. Usually it's like 0.05. Oh my gosh, why does that always do that? That's a pretty common significance level. And what that means is that they were okay with a less than 5% chance that this could happen at random. Like if it's more likely than 5% that this can happen at random, then they will accept the null hypothesis. If it is less probable than 5%, then we're going to reject the null hypothesis. Remember, ours was way smaller than 0.05. It was 0.00003, which is way smaller than 0.05. If the probability is less than the significance level, you reject the null hypothesis. All right. You're like, no, this probability is way too small. This can't possibly be true. We're going to reject the null hypothesis. Is rejecting the null hypothesis the same as proving the alternative hypothesis? No, that isn't how things in statistics work. Rejecting the null hypothesis means that there isn't sufficient evidence to conclude that the null hypothesis is a correct belief. And you have to be careful how you say that. It's also important to note that not rejecting the null hypothesis doesn't mean it's definitely true. It just means that the sample data has failed to provide sufficient evidence to cast serious doubt on its truthfulness. All right, let's do another example. The mean age of graduate students at a university is at most 31 years, with a standard deviation of 2 years. A random sample of 15 graduate students is taken. The sample mean is 32 years, and the sample standard deviation is 3 years. The p-value is calculated to be 0.0264. For this example, you're going to state the null and alternative hypotheses and interpret the p-value. Are the data significant at a 1% level? So this has enough information that you could go calculate the p-value, and we're going to be calculating p-values, don't worry, in the next section at the end of this week. But for now, I want you to just be able to interpret what you get from those, so you're looking at the overall big picture of what's going on here. Let's start with stating the null and alternative hypotheses. All right, the statement is that the mean age, so we're talking about a mean age of graduate students is at most 31 years. All right. The mean age of graduate students is at most 31 years. That means less than or equal to 31. What does less than or equal to tell you? That tells you that's going to be the null hypothesis. So the null hypothesis is that the mean age is less than or equal to 31. And the alternate hypothesis is that the mean age is greater than 31. All right. Let's interpret the p-value. Well, the p-value is 0.0264. All right. So what does that mean? It means that the probability of the sample mean being 32 years, which is what we have, the probability of it being 32 years, assuming that the population has a mean age of 32 and a standard deviation of 2 years. So if we look at that normal distribution and we say the probability of our sample mean being 32 years, the probability of that happening is 0.0264. All right, that's what the p-value is. And so the p-value is actually greater than the significance level. They asked you for a 1% significance level. My p-value was about 2%, which is greater than 1%. And so no, this data is not significant at the 1% level. We accept the null hypothesis to be true, and we cannot conclude that the mean age of graduate students is not at most 31 years. All right? So what did we do here? We got a p-value that was greater than our significance level. So that tells us we're going to accept the null hypothesis. There's a nice little mnemonic device to help you keep this clear. If the p-value is low, the null must go. If the p-value is high, the null must fly. So what does that mean? We just did the second one. The p-value was high, the null must fly. That means we accept the null hypothesis because the p-value was larger than the significance value. On the bread one, the p-value was low, and we rejected the null hypothesis. The null must go, right? So that is p-value is less than alpha for the first one. P-value is greater than alpha for the second one. Let's do one more example. A pharmaceutical company claims their drug prevents a disease 78% of the time, and doctor disputes the claim. Let's go ahead and state the null and alternative hypotheses. Then a hypothesis test is conducted at 5% significance level. If the p-value is 0.035, what conclusions can be made? All right, so what would be the alternative and null hypothesis for this example? The company claims their drug prevents a disease 78% of the time, all right? So 78% or more, p is greater than or equal to 0.78. It's a population proportion, not a mean. So we're doing a proportion example. And so the alternative hypothesis is that p is less than 0.78, right? A hypothesis test is conducted at the 5% significance level. This tells us alpha equals 0.05. Okay. What was our p-value? 0.035. Is that more or less than alpha? All right. Well, 0.035 is less than 0.05. The p-value is low. The null must go, right? That means we are rejecting the null hypothesis. Reject the null. The p-value is too small. It is too improbable that this p-value happened for this test, whatever it turned out to be that they did some samples and whatever. But what happened was too improbable to happen for a 5% significance level. All right. So the doctor concludes that fewer than 78% of the time the drug prevents disease. All right. Well, I hope this was helpful to you. The next thing we'll be doing for the end of this week is actually doing some hypothesis testing.